Hello, this is Deep Thoughts with Deegan, and today I'm going to be talking about fractional derivatives, including complex, negative, and all of them. Obviously, I'm not going to do all of them today, but I'm going to show you how to find them. We'll go from there. All right, let's get started. So when we're talking about the nth derivative of a function, we're trying to find the nth derivative of e to the x. Right, easiest way to do that is you just see, all right, what's the derivative of e to the x? What's the antiderivative of e to the x? And e to the x is the most simple example of all of these. There's a lot more I'm going to cover today, but e to the x is the most simple because if you look here, whenever you have it in a derivative or antiderivative, it contains itself. And because I'm only talking about antiderivatives, I just have the integral here for the notation. I'm not going to worry about the plus c yet. It will become important later. But for this case, it's not going to matter a ton. Now here, we got, these are the same. It contains itself. So if I were to take the derivative of this, of e to the x, e to the x. Second derivative of e to the x is going to be the derivative of the derivative of e to the x. Also e to the x. No matter how many times you do that, it's always going to be e to the x. Same thing here. The 51st derivative of e to the x, also going to be e to the x. It's all going to be the same. Now, there's a couple ways we can write this out. Let's just start off with saying, in our case, f of x is equal to e to the x. There are three types of notations that I might use. One of them I made up. The first one, though, probably the one that I'll use the least, is this right here, where I'm going to say the nth derivative of the function f of x in this form, where we have f n x, is, in this case, it's equal to e to the x. Nth derivative of f of x is equal to e to the x. Same thing right here, where we got dny over dxn of f of x. These two mean the exact same thing, equals e to the x again. Now, for my own notation that I use, there's three parts. There is the nth positive derivative of the function f of x. In this case, it's going to be equal to e to the x. This just means as we take one more derivative in times, what is it going to look like? But also, right here, we can take the nth antiderivative of the function, which is e to the x. Now, if I were to put this all together up here, the way I would write it, I forgot the dx's down here actually. The way this notation usually works is if I'll plug in the dx right here. Because otherwise, this is how you know the variable you're integrating with respect to. You could also do partial derivatives with this, I think. I've just never done that. So now we can say here, the nth derivative of e to the x with respect to x is equal to e to the x. The reason we can say this is because these two match perfectly. No matter how many derivatives you take, positive derivatives, so 1, 2, 3 derivative, it's going to be the exact same as the amount of derivatives you go down, the antiderivatives. So the nth derivative of e to the x with respect to x is just going to be equal to e to the x. So now I'm going to look at other exponentials. Right here, we got e to the ax, the nth derivative of e to the ax with respect to x. Now, this looks a little scarier because it's not just going to be e to the ax. But let's just start with finding the positive one. So to do that, I usually start with taking the first derivative, right? First derivative, e to the ax. This is chain rule, right? So we're going to have e to the ax as our outside function, ax as our inside function. What that's going to look like is, this one's pretty self-explanatory, so I'm not going to work out the whole thing, but it's a e to the ax. Now, a is a constant, so we can take it out. So if I were to take the derivative of a e to the ax, it's actually equal to a times the derivative of e to the ax. And as you do this, it's going to come with that out again. So we'll take the a out every single time. Now, if I go down here, I'm just going to say the nth positive derivative of e to the ax now with respect to x is going to be equal to a to the n, because it's going to multiply in every single time, e to the ax. There we go. Putting over here, I know there's a little bit of a glare, but I'll go back to that in a second. Now, get my thing here. Now I want to try integrating it n times. And like I said before, I'm not going to include the plus c yet. So right here, this is just actually going to be a u sub integral of e to the x with respect to x. So that's just going to be, I'm not going to do this one either because this one's pretty self-explanatory. It's going to be 1 over a e to the ax. Now, it's going to have the same general thing happen, where we're going to go e to the ax is going to go towards, as you take more integrals, antiderivatives, it's going to be 1 over a to the n e to the ax, which is equal to a to the negative n e to the ax. So now, right here, I got the nth antiderivative of e to the ax with respect to x is equal to a to the negative n e to the ax. But those don't match. They actually do, because when we're taking the antiderivative, we're going down. So what we do is we're going to take this negative n, and we're going to flip the signs. We flip the signs of all of the n's from the antiderivative to get here. And look at that. If we change that to an n, a positive n, these are the exact same. So we can actually say this is a to the n e to the ax. So here there's a few general rules where we have a sum or difference. Obviously, because integrals and derivatives both do this, when you have the nth derivative of f of x plus or minus g of x with respect to x, it's going to separate those into two separate ones. Also, if we have a constant coefficient right here, it just comes outside of the term. Right here also, here's a generalization of exponential functions. All of them work like this, as long as a and b are constants. This is worked out exact same way as the e to the ax. But with this information right here, we can actually find the nth derivatives of the sine and cosine functions. Now this one looks a lot more difficult. It's a little bit more difficult. The nth derivative of sine of theta with respect to theta. Right, I'm just using theta because it's a sine function. To do this, we're doing this a little bit of a different method. So before, we just looked at what happened with patterns. With this one, we have to apply those patterns. Right here, it's a little hard to see, but I have Euler's formula for sine of x, where we have e to the ix minus e to the negative ix over 2I. So I'm actually going to take that down here, where I have the nth derivative of e to the ix minus e to the negative ix over 2I with respect to x. I'm going to take out this constant down here at the bottom, 1 over 2I times the nth derivative of e to the ix minus e to the negative ix with respect to x, right? This I can take down further, right? So my final result is going to look something like this. The nth derivative of sine theta d theta is equal to 1 over 2I, nth derivative of e to the I theta minus e to, actually no, I'll split it apart. That's what I forgot to do. D theta minus the nth derivative of e to the negative I theta. That's a really bad I, but you get the idea. D theta. This right here is what it's going to look like. Now for the first part of that, the nth derivative of e to the I theta with respect to theta, right? So what I'm going to do is I'm going to take up a lot more space than this. I'm going to go over here, and if we remember, the nth derivative of e to the ax is equal to a to the n e to the ax. So I'm going to say that's going to equal I to the n e to the I theta. Now, kind of what that looks like is it's kind of just going in a circle, and that's a weird way to go in a circle, but that's what it's going to do, basically. It's going to just be rotating. That's what I does. But from here, I'm going to do something kind of weird. I'm going to put it in a different form that's the exact same. We're going to take e to the ln of this, the natural log of this whole thing, I to the n, e to the I theta. And I can actually split this apart into e to the ln of I to the n, e to the I theta. Yeah, e to the I theta. Because when I'm taking this apart, it's going to be e to the ln of e to the I theta. That's going to cancel out, so I'm just left with e to the I theta. That's fine. Now, right here, I'm just going to go over here and do, well, what's the ln of the natural log of I to the n? N natural log of I. You're not supposed to have anything that's not a positive number, a positive integer. What does that mean? Integer? A positive real number in here, right? Well, actually, you can have a complex one right here. So the natural log of I is equal to pi over 2. So right here, the natural log of I to the n is going to equal n pi over 2. I forgot the I. There's an I on the end. N pi over 2i. Now I'm going to go back over here. I'm going to plug that in. We're going to have e to the I times n pi over 2 times e to the I theta is equal to, we can combine it. So we add these together. And when we do that, we can get e to the I theta plus n pi over 2. Now, that's meant to represent this term up here, the e to the ix, the derivative of that. And if you look here, the x is just replaced by the theta plus n pi over 2. Now, the same thing is going to happen when we try to do e to the negative I theta. But it's the exact same steps, except the natural log of negative I is equal to negative pi over 2i. Like that. So, the nth derivative of e to the negative I theta right here, e to the negative I theta, is just equal to e to the negative I theta plus n pi over 2. And if you notice, right here, we want the x's to be the same, right? And they are. Theta plus n pi over 2. So if you were to plug these in, sine theta, d theta, and the derivative of that is equal to sine of theta plus n pi over 2. Same thing happens with cosine theta. The calculation is slightly different, but the method's the exact same. Right here, though, I'm trying to find the nth derivative of tangent of x. You can't, because if you look right here, we get secant squared. Right here, 2 secant squared tangent. And then right here, 2 secant to the 4th plus 4 secant squared tangent squared. It just keeps getting bigger, and you can't really predict how it's going to do that. And to solve this, what I do is I just create my own little functions. So I have 3, because there's 3 of them you can't do. So omega alpha of 2 functions u, v, dx is just the product rule, the nth product, right? Now, if I'm going to do beta, the omega beta of u over v dx, that's quotient. And then my last one down here, sorry, this is really bad. If I'm going to have f of v, where v is still a function, dx. So we basically have a composition of functions here. That is just going to be the nth chain rule. The reason I use these functions is because sometimes you can simplify things with them. But for here, the best way I can describe the tangent function is omega beta of sine theta over cosine theta with respect to x, or theta. That's kind of the best way you can describe that. I've tried many of these in a row, and it doesn't go anywhere. So this is really the best way to do it. So if you were to plug these in, sine theta, d theta, and the derivative of that is equal to sine of theta plus n pi over 2. Same thing happens with cosine theta. The calculation is slightly different, but the method's the exact same. Right here, though, I'm trying to find the nth derivative of tangent of x. You can't, because if you look right here, we get secant squared. Right here, 2 secant squared tangent. And then right here, 2 secant to the 4th plus 4 secant squared tangent squared. It just keeps getting bigger, and you can't really predict how it's going to do that. And to solve this, what I do is I just create my own little functions. So I have 3, because there's 3 of them you can't do. So omega alpha of 2 functions u, v, dx is just the product rule, the nth product, right? Now, if I'm going to do beta, the omega beta of u over v dx, that's quotient. And then my last one down here, sorry, this is really bad. If I'm going to have f of v, where v is still a function, dx. So we basically have a composition of functions here. That is just going to be the nth chain rule. The reason I use these functions is because sometimes you can simplify things with them. But for here, the best way I can describe the tangent function is omega beta of sine theta over cosine theta with respect to x, or theta. That's kind of the best way you can describe that. I've tried many of these in a row, and it doesn't go anywhere. So this is really the best way to do it. Now let's look at the power rule. Power rule. So for the power rule, it's actually a little more complicated than the other ones. You have to look at the patterns more critically. So I just have x to the 4th here, right? You take out the 4, now it's x to the 3rd. Take out the 3, 4 times 3, x squared. You keep going, you just multiply in the number under it. That's the factorial function. But as you can see here, it doesn't contain all of them. So the best way for me to explain this is for me to just write out all of these, right? So if we want this 4 times 3, right? And we're going to start by saying that is 4 factorial. I don't want these 2 in here. So what I can do is I can divide by just these 2. Don't care about these. That is 2 factorial. And right here we can see this is the second derivative, right? So we always want to start with this a. So we're going to start with a factorial, right? That's going to be divided by, we're going to start at a, and we're going to subtract the amount of steps we have. So we go 1, 2 steps. This is what's left over. A minus n factorial. That's how we get the coefficient. Then we get our variable. And the power is just going to be our starting point minus the amount of steps we've taken. Now, I'm going to take this one step further because this only works for integers. What I'm going to do now is going to take this. I'm going to use something called the gamma function. Now, the gamma function looks like this. It's capital gamma of z is equal to the integral from 0 to infinity of t to the z minus 1 e to the negative t dt, right? Kind of scary. I'm going to erase this down here while I'm explaining. This looks kind of scary. I have never once in my life used this in this form. More useful form is this. Gamma of z plus 1 is equal to z factorial. The reason I'm using z is because it represents a complex number. So now we can plug complex numbers in there. So I'm going to put that back. This right back where I have a factorial divided by a minus n factorial x to the a minus n. And if we recall, gamma of z plus 1 is equal to z factorial, right? I can turn these into the gamma function, where I like to start on the bottom when I'm doing these, where I have a minus n for the factorial plus 1 in the denominator. That's fine. I can deal with that. Now the numerator, a plus 1, gamma of a plus 1. On the outside, it's still a minus n. See? This is sometimes you have to bring in external things to make this work. But that's how this looks. And now, because I feel like this is a great place to do this, now I'm going to talk about taking the nth integral. Now I'm going to explain this right here. So let's say we want to find the nth integral of f of x with respect to x. Here we got our nth antiderivative, but also there's going to be this summation right here, which is supposed to be this right here. Just going to do dot, 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 because I don't want to rewrite the whole thing. So as you can see right here, let's say we have 1, something pretty simple, right? The derivative of that is going to be x plus c, right? We take the antiderivative, the integral of 1 plus x plus c. Sorry, I got distracted because I forgot the dx. It's going to equal this, 1 over 2 x squared plus cx plus c1, because we have a different c. Now what I'm going to do here is I'm going to say each of these are c0. It's going to look like this formula right here. This is actually just the power rule, but inverse. Not inverse, it's just backwards. So we're going to start at j equals 0, so c0. And for this step, n is also equal to 0. We're going to say this is the 0th derivative. We got 0 plus 1 is 1. 0 plus 0 plus 1 is 1. So it's just 1. So it's c x to the 0. It's just c, right? This right here. If we plug in 1, it's just going to be c1 x. Plug in 2, c2, well, 1 over 2, c2 x squared. It's going to keep going like that. So we can just add that in right there. Now for this last example I'm going to do, I'm going to show how you can use these kinds of patterns for all sorts of functions. Right here, I have x e to the x. To start with, I'm going to take the positive nth derivative, and I'm just going to start with a product rule. So d over dx of x e to the x, it's just going to be a pretty simple product rule. It's just going to be e to the x plus 1, right? So for this first derivative, when I do these, I like to keep track of the number of derivatives I've taken. It's going to become x e to the x plus e to the x, right? Funny thing is, now I know the derivative of this, we can just add that in, and we already know the derivative of this. So now if we take that, we get x e to the x again plus e to the x, because we're just taking the derivative of that. Do that. Plus e to the x from here. X e to the x plus 2e to the x. No matter how many times I do this, I'm just going to get x e to the x plus n e to the x. Now, a little bit more difficult, but not too much worse. Now I'm going to do it in the opposite direction. So now I'm going to look at the nth antiderivative of x e to the x. To do this, I'm going to use integration by parts. So I'm going to say the integral of x e to the x with respect to x, that's one of the worst x's I've ever done, but that's okay. It's going to be equal to u is going to be, u is equal to x, e to the x is going to equal to v. So it's going to be x e to the x minus the integral of e to the x dx, right? And so for our first one, it's going to equal x e to the x minus e to the x. Very similar to what it was before. Take it again, we get x e to the x minus e to the x. Right here, negative e to the x, the derivative, the antiderivative of that is going to be e to the x. So that's going to be equal to x e to the x minus 2e to the x. Same thing here. Now we have x e to the x minus 2e to the x. Okay, so now I have that. I'm going to write both of them down, right? So I got the nth positive derivative of x e to the x is going to equal x e to the x plus n e to the x, right? And the nth antiderivative of x e to the x, I keep forgetting these dx's, is equal to x e to the x minus n e to the x. Now remember, if we flip this sign, what's that going to become? X e to the x plus n e to the x. So actually, these do match. These actually match. So, bam. I can prove now that the nth derivative of x e to the x with respect to x is equal to x e to the x plus 2e to n e to the x. I don't know why I wrote a 2. N e to the x, no matter which direction you go. So that's going to be in this video. Thanks for watching. Do all of the things like subscribe, comment, and let me know what you thought, and see you next time.